Hi, my name is Westin, and I'm in CHEM 6BL here at UCSB. And today I'll be doing my cooking assignment. I'll be creating a pH indicator out of a compound in Red Cabbage. So pH indicators are compounds that change color based on the pH of the solution added. Now, obviously, we know pH, the lower the pH, the higher the concentration of H plus or hydrogen ions, so it's more acidic. And then the higher the pH, the more basic, the lower the concentration of H plus. So pH indicators will just tell us the relative concentration of H plus based on the color. So red cabbage, like other vegetables, has a water-soluble pigment known as anthocyanin. And this compound is similar to other compounds that we've seen in this class, similar to the methyl orange lab, for example, and other labs, but it's a highly conjugated system. So it has a network of delocalized electrons where it's like alternating single and double bonds, so that those pi orbital electrons are delocalized throughout, and they can absorb light of specific wavelength. And this wavelength happens to be in the visible light spectrum, so we can see it with our eye. So whatever color they absorb, a color complementary to that will be seen with our eyes. So what I'll do today is I'll take some red cabbage, add it to some hot water, and put it in a blender and blend it up. So the blender is just to mechanically break up the tissue of the cabbage to extract that anthocyanin, and then the warm water is just so it's more soluble in it. We're just trying to basically get a solution that we can add our compounds into. So whenever a compound with a pH below the pKa is added, it's going to protonate the anthocyanin. So it'll give that anthocyanin a positive charge. And then whenever the pH of the compound added is higher than the pKa of anthocyanin, it's going to deprotonate the anthocyanin and give it a negative charge. And these changes will have an effect on the conjugation of the molecule. So we know from methyl orange and other labs, but highly conjugated systems have a smaller difference in their ground and excited states. So that means less energy is required to excite those electrons into the excited high energy state. So that means they'll absorb lower energy light to jump that gap, and lower energy light will be longer wavelength light. Okay, so that's our red and our orange being absorbed. So we're guessing it's gonna appear green or blue because that's complementary. And then compounds that are less conjugated are going to have a larger difference between their ground and excited states. So it's going to take more energy to excite them to that high energy state. So they're going to absorb higher energy light, and higher energy light is shorter wavelength. So in this experiment, it's going to be green and yellow type light. So it's probably going to appear red and purple. So we'll see in this experiment that acidic low pH solutions are going to cause the pH indicator to turn red. So that means it's absorbing green light, which is around 520 nanometers, give or take, but a wavelength something around there. So that means that's higher energy light than the basic counterparts. So that means when it's protonated, when anthocyanin is protonated, there's less conjugation because there's a larger gap, because it's taking that higher energy light to excite it. So that larger gap is telling us there's less conjugation in the system. So because it needs higher energy light to be absorbed to make that jump. So it's a less conjugated system when it is protonated with an acidic solution. So the opposite can be said for basic high pH solutions. We're expecting them to turn a blue and even It can even turn yellow, which is a different example because there's different types of anthocyanins, but it can turn yellow with bleach. But we're going to expect it to turn blue with a relatively basic solution. So that's going to correspond to around 620 nanometer wavelength light. So that means it's absorbing lower energy light because it's longer wavelength. So that means there's a smaller gap between the ground and excited states. So it takes less energy to excite those electrons. So that means it's when it's deprotonated with this basic solution, there's more conjugation because it's that smaller gap. So it's more conjugation. So then we can follow these trends and then rank our chemicals added from acidic to basic, going from red being the most acidic, and then blue, and then even to yellow being the most basic. So here I have some warm water in the blender, and here's some red cabbage. So I'm just gonna throw this in here. And then I'll blend it up and then I'll come back. So now that we've blended the red cabbage, we're gonna filter it just to get all the big chunks out into separate containers. So here's some muriatic acid with literature value pH around 1 to 2, so it's supposed to be very acidic. So let's see what happens. And a bright red color. So I've squeezed some lemons into this cup right here, and I'm gonna do the same thing. Again, another bright pink red color. So here I have some coffee, and I'm gonna add it and see what happens. So it looks red, but a little darker, but that might just be due to the dark color of the coffee. So here I have some baking soda, which is just sodium bicarbonate, and it's a solid powder, but I just added a little bit of water, and we're gonna add it and see what happens. And a bright blue color. So here I have some bleach, which it says it's sodium hypochlorite in this cup right here, and let's see what happens. Ooh, a nice yellow color. So these results followed our predictions for the most part, with the acidic compounds absorbing the higher energy light, meaning the anthocyanin was less conjugated, and the basic compound absorbing the lower energy light, meaning the anthocyanin had more conjugation. The bleach turned the anthocyanin yellow, which corresponds to absorbing the highest energy light, meaning the anthocyanin it was acting on had the least conjugation of all compounds observed. So there are multiple types of anthocyanins. So the most likely explanation for this phenomenon is the bleach was so basic that it deprotonated a different type of anthocyanin that was being observed in the previous example. So this particular anthocyanin that bleach was acting on, deprotonation must have caused it to have far less conjugation, and then correspondingly a larger energy gap between ground and excited states, because it was appearing a yellow color, which means it absorbed very high energy short wavelength light around 410 nanometers.